Okay. Today, we are going to be doing thermochemistry, which can be a little bit boring, but maybe you will find it interesting. Okay, so a few definitions. Entropy is a measure of the amount of energy that is unavailable to do work. So it's just the disorder or the randomness of a system. Like a messy room would have more entropy than a clean room. And in closed systems, entropy always increases with time. And the symbol for entropy is S. Heat is the energy that is transferred as a result of difference of temperature. And the symbol for it is a lowercase q. Enthalpy is the total heat of a system, and it's delta H. Temperature is the average kinetic energy of a system, either Celsius, Fahrenheit, or Kelvin, but in science we like to use Celsius or Kelvin. And Kelvin is just Celsius, it has the same increments, but it starts at absolute zero instead of the freezing point of water. And energy is the capacity to do work. Energy is measured in joules or kilojoules most of the time, so as a result, most of the other ones like heat, enthalpy, entropy, they're all also measured in joules or kilojoules. So here are a couple of diagrams. So entropy is the disorder of a system. So as the temperature increases, there's more entropy. So gases have more entropy than solids. And to the right of that, you can see a difference between a high temperature substance and a low temperature substance. So the higher the temperature, the more average kinetic energy there is. So that's why the tails are so much longer because they're moving a lot faster. They're all vibrating a lot more than a lower temperature, which is moving less at a slower pace. Enthalpy is like the total heat. It's like taken in from the environment or released out. And I didn't mention this before, but it's very important to know that most of these can be positive or negative. Like heat and enthalpy can be positive or negative depending on if it's being released or absorbed. And so can energy. Energy can be positive or negative depending on if the energy is being absorbed or being released. So types of heat transfer. Uh, in your everyday life, there are going to be lots of examples of when heat is being transferred between two different things. So conduction is when energy is transferred through direct contact. So it's when the molecules are colliding with each other, transferring the kinetic energy through the collisions. Because every time there's a collision between two molecules or atoms or whatever, think of it as like pool balls. The faster one loses energy to the slower one, and the slower one becomes faster. So that's why energy always flows from high to low. Convection is when heat flows through a fluid like a liquid or a gas. So as it warms up, it gets less dense and flows to the top. And then it cools down and sinks again, forming the convection cycle. And this is prevalent a lot in real life. Like magma, it's what causes the continents to move and the atmosphere and soup. Radiation is the transfer of energy through waves. No contact is needed. So like the sun transfers energy to us through radiation. So in this diagram on the bottom, you can see that the person touching the handle, that's conduction because it's direct contact. Whenever there's direct contact, then conduction. And inside the soup, that's convection because whenever there's a fluid, it's probably going to be convection. And as you can see, when it's at the bottom, it's close to the heat source, so it heats up, but it gets less dense and flows to the top where it's further away from the heat source. And radiation, you can see that there's no direct contact. It's coming from the heating coils, and the heating coils are getting super hot, and then it's transferring through infrared rays. So some real life examples of heat transfer. Uh, okay. Ice cream. When you're making ice cream, you know how you're like spreading the code? You're not actually doing that because remember, energy can only disperse from high to low. So you're actually like dispersing the heat. You know how you put a spoon into hot food and then you can feel it become hot? That's from conduction because the food is touching the spoon, which is then getting hot, and then that's going into you, and that's auto conduction. And convection ovens. Technically, all ovens are convection because they all have air inside, and air is a fluid. But convection ovens just have fans inside to help this process. So they circulate the air, which is convection, and that allows it to keep a more consistent temperature throughout the oven since the air that's being heated is like always different, you know? Okay, so Q equals mc delta T. This is a pretty important equation that is used a lot in thermochemistry. So what it means is heat equals mass, which is usually in grams, times the specific heat times the change in temperature. And delta in science just means the change of. So if it's delta V, that's the change in velocity. If it's delta D, that's the change in the displacement, you know? And specific heat is a new concept that we haven't introduced yet, but specific heat is the amount of energy it takes to raise 1 gram of material by 1 degree Celsius. It doesn't need to always have to be 1 gram in 1 degree Celsius, but for our purposes, it will be. And remember how I said that when you add salt to the water, the boiling point elevates and gets higher, but it doesn't exactly become faster to, it doesn't become slower to boil. That's because when you add salt to the water, the specific heat is also lowered, so it takes less energy to heat the water up. So although the boiling point is higher, it also can heat up faster. Okay, so these are some relative specific heats. Water is 4.18 joules per gram Celsius, which is really, really big. And this has a lot of real life applications. Like we use water a lot for coolants, like in nuclear facilities, they use water to cool everything down because it can absorb so much energy without even like getting hotter. It just absorbs the energy. Dry air, which is like no water inside, is around 1, and iron and most other metals are pretty low. Iron 0.45 joules per gram Celsius, which you can feel this in real life because like when you touch the metal versus if you touch wood, the metal feels cooler even though it's the same temperature as the wood. And that's because the specific heat is so much lower, so it absorbs the energy and then it gets like hotter, you know? It gets it is more sensitive to changes in temperature. Energy is always consumed. Energy cannot be created nor destroyed, which is very important in physics and chemistry. And so, because of this, when you're solving for the final temperature of a system, the Q of both equations has to equal 0. And we'll use that more later on. Okay, states of matter. There are 3 main states of matter. There's also like a bunch of other ones that we don't use because they're not really applicable to real life. But there's solids, liquids, and gases. So solids, they have the least kinetic energy. They're the coldest. Liquids are in the middle, and gases have the most kinetic energy, and therefore they are the hottest. Solids are highly structured. They usually have like, unit cells or crystalline structures. So they have a definite shape and a definite volume. This means solids, they're built the way that they are. You can't change the shape or the volume of it. liquids flow freely, but they're still bound together by those intermolecular forces that we talked about last time. And so they have a definite volume, but indefinite shape. So like the water in this cup takes the shape of the cup, but as soon as I spill it, it's a new shape. It's still the same volume though all the time. Gases, the molecules move freely. They're not bound to each other at all. And gases have the highest kinetic energy and therefore the highest temperature. They have indefinite shape, indefinite volume. They take the shape of the container and also the volume of the container. And this is why the higher the intermolecular forces, the higher the boiling point is going to be, because it has to overcome all those intermolecular forces in order to like break free. So remember with specific heat, it takes that much energy to raise the 1 gram by 1 degree Celsius. So as you add more heat, the temperature tends to increase. But when you reach the transition points between like the different states of matter, they plateau. And that is because the energy that's being added to the substance, it's not being used to raise the temperature anymore. It's used to transform that material from one state of matter to the other. So like solids, you can see they're highly structured. Liquids, they're still bound to each other, but they're not as structured. Gases, they're just free. So when you add that extra heat or energy, you're like helping to bounce around more. And remember, temperature is just average kinetic energy. So the temperature will usually increase, but when you get to those transition points, it's using them to like break it off. Like for liquid to gas, it's using the energy to like break apart the liquid and to like turn it into a gas. So the latent heat of fusion is the amount of energy it takes to raise that substance by 1 degree Celsius. I mean, it takes to convert 1 gram of solid into liquid. And latent heat of vaporization is the amount of energy it takes to convert 1 gram of liquid into gas. So they're pretty similar to specific heat. Okay, boiling versus fried. So the boiling point of water is a lot lower than oil. Oil is much higher than 100 degrees Celsius or 212 degrees Fahrenheit, which means that oil can cook the food faster than water. And most foods cannot get over 100 degrees Celsius because as you heat it up further than that point, the energy will start to be used to make the water evaporate instead of making the water like get hotter. Okay, so this is an energy diagram of a reaction. So chemical reactions, they don't just happen. They take energy to happen most of the time. So see here, that is the energy of the reactants. E is the potential energy of the products. And A is the activation energy. The activation energy is the energy that you need to collide in order to overcome like the forces that's holding the molecules together to like break them apart and create new bonds. And B is delta H. That's the change in heat, or that's the entropy. Okay, so there are endothermic reactions and there's exothermic reactions. Remember, energy cannot be created or destroyed. So for A, you can see that the potential energy of the products are higher than the reactants. That means you need more energy to get to those products. But the energy cannot be created. So the energy is taken in from the surroundings. And B is the opposite. The products is lower than the reactants. The reactants have more potential energy. So the reactants, when they react, they have less energy than before. But energy can't be destroyed. So it just releases those energy to the environment. So an example of an exothermic reaction would be fire. You can feel that it's releasing heat as the reaction progresses. an endothermic reaction would be like those cold packs that you squeeze. When you squeeze it, it's like you're mixing the two liquids, and those liquids are reacting in an endothermic reaction. And because the products have more energy than the reactants, and it needs to absorb that energy. So the energy is absorbed through you or whatever the ice pack is touching. Okay. Hess's law. So in reality, reactions are often done in steps or elementary reactions. And Hess's law states that the same reactants and products, for the same reactants and products, the change in enthalpy will be the same regardless of the path taken. So if you have, on the screen, if you have a nitrogen gas and oxygen gas, and you try to turn it into nitrogen dioxide, it doesn't matter if you go through this elementary step first, or if you just go there. The change in heat, the enthalpy is still going to be the same, because the reactants and the products are always the same. Okay, total energy equals work plus heat. Okay, I'm gonna take the time to answer any questions or go back to any slides that you guys want to go back to. Okay, so the triangle, that's the Greek letter delta, or that's like Greek letter delta. And in science, that just means the change in. So change delta T is just the change in temperature. Okay, yeah. This slide or the other one? Okay. So the total energy equals the work plus the heat. So work, I don't know if I explained this yet, but work is like kind of like, hang on. Work is like the transfer of energy, and heat is the transfer of energy due to the temperature. So let's say if you have, and work can also be positive or negative, depending on if it's done by the system or onto the system. So let's say you have 600 joules that's done on the system, and 300 joules of heat is leaving. So the total internal energy would be 300 joules then. Okay. Okay. If you guys don't have any more questions, then we're going to do some problems now. Okay. You can type in the chat if you want, or you could just think it in your head. Doesn't really matter. Okay, so this one is B. The average kinetic energy of the system. So let me explain. Enthalpy is the total heat of the system. Temperature is the average kinetic energy of the system. So like hotter water, the water molecules are moving a lot faster and bouncing off of each other more than in cold water. So the hot water has more temperature. And heat is like the energy that's being transferred because of a difference in temperature. So like heat, the bigger it is, the more heat it has for the most part. So like a giant ice cube has like more heat than a small ice cube. But for temperature, they would have the same temperature because temperature is the average kinetic energy. And Celsius is just a unit of measure for that, for temperature. Okay. Okay, yes, this one is radiation because there's no direct contact. So that's how you can tell that it's radiation. Okay, so this one is false. The heat of fusion is the amount of energy it takes to convert 1 gram of solid into liquid. The liquid into gas one is the heat of vaporization. So that's just vocabulary. Okay. I have more problems that we can do. Oh, sorry guys. Okay. Basically, so when you squeeze the stuff from the higher pressure, all the molecules are forced to get closer together to each other, which can help like change states. So the lower the pressure, the less they're being squeezed. So that's why it's easier to go from liquid to gas at higher altitudes where there's a lower pressure. Okay, two, you guys can type number 2 into the chat. Okay, yeah, I'll answer your question, Chi. So pre-AP Chem, that's usually like, are you in high school? So that's usually like first year chemistry, so that's going to be an introductory course. So you won't really need to do anything to prepare for it because it's going to start from the very beginning anyways. But it's cool if you want to prepare earlier, then you could do like Khan Academy. Organic Chem Tutor is really good. Yeah. Okay, yeah, you're right. The specific heat of water is special because it's really high. It's abnormally high, so it takes a lot of heat or energy to raise the water's temperature. Okay, let's do number 3 now. And I'm going to drop the link to the slides in the chat if you want to look at it. Okay, so solids are the coldest, liquids are next, and gases are the hottest. Solids are definite shape, definite volume. Liquids are definite volume, indefinite shape. And gases are indefinite volume, indefinite shape. Okay. Number 4. You guys can think about this. Okay, so for number 4, there's conduction, convection, and radiation. Radiation, that's like the sun, fire, stuff like that. Convection, well, one, it's in the atmosphere a lot, and 2, it's like when you're cooking soup, like there will be a cycle kind of. And conduction, it's like whenever I touch something hot and get burned, that's conduction. Okay, number 5. For this one, you have to use Q equals MC delta T, and I'll drop the specific heat of water into the chat for you guys. Okay. So for this one, you'd use Q equals MC delta T. So Q is heat. So you just do mass times the specific heat times the change in temperature. So the mass here is 100 grams times the specific heat, which is 4.18, times the change in temperature, which is 20, and that multiplies out to 8,360 joules. Okay, number 6. How much energy will it take to melt 10 grams of water? Okay. Okay, how does melting water work? So when you're melting water, you're like adding more kinetic energy to the ice. So then eventually, like you break the structure of the ice because the ice has like a very like crystalline structure from the hydrogen bonds. So when you add that extra energy, you're like breaking up the hydrogen bonds, or which is an intermolecular force, and you're overcoming that force to break them free, and then it turns into a liquid where they're still bonded together, but like they're not in a structure anymore, if that makes sense. So water has a pretty high heat of fusion because of those hydrogen bonds that are very hard to overcome because it's the strongest intermolecular force. So for number 6, you would just multiply the heat of fusion times the grams, which will give you 3,440 joules, which shows you it takes a lot of energy to melt water. Okay. 7. Name the heat transfers shown in the diagram above. Okay, yeah, if you missed the beginning of class, all of the recorded ones will be on the KTK website later. No problem. Okay, so for this one, number 1 would be convection, number 2 would be conduction, and number 3 would be radiation. So how you can tell is number 3 is no direct contact, number 2 just direct contact, and number 1 it's in a fluid that's like going through the cycles. Okay, which has the lowest kinetic energy, solids, liquids, or gases? Yeah, so this one's solids. Solids have the least kinetic energy and gases have more kinetic energy. Okay, number 9. Okay. We'll do number 10 first. So when 1200, 1250 joules is added to 4 kilograms of metal, it all melts. What's the heat of fusion of this material? And one kilogram is equal to 1,000 grams. Because you need to use grams in the equation. Okay. So you just need to manipulate this equation around, because for this one, it's Q equals the mass times the specific heat of fusion. And if you're trying to find heat of fusion, you just have to divide the energy by the mass. So it's 1,250 joules divided by 4,000 grams, because then you convert kilograms to grams, which gives you 0.3125 joules per gram Celsius. Okay, for number 10. This one is pretty complicated, so I'll work through this with you guys. So the 30 degrees Celsius water is going to increase, and the 50 degrees Celsius water is going to decrease in temperature, right? Because equilibrium would be somewhere in between those. Room temperature as a continue cooling to room temperature. Okay, well, we're assuming that's like a closed system, so it like isn't affected by the room temperature. But okay, so the Q and the Q, they're going to add up to 0 because energy cannot be created nor destroyed. So the total heat of the system has to be 0, right? Okay, so for the 30 degrees Celsius one, it's 10 times 4.8 times 30. For the other one, it is 40 grams multiplied by the specific heat, and this will be 50 minus T, because remember that delta sign means that it is the change of something. So the change in temperature is going to be that middle temperature minus the lower temperature or the high temperature minus the final temperature. So because the heat will add up to 0, because energy cannot be created nor destroyed and it's a closed system, you can just add these two, and then on the other side is 0, and then solve for T. So this will be 41.8 times T minus 30 plus 167.2 times 50 minus T. Okay. Is everything okay? Okay. I think I accidentally left in the middle of it. I'm just going to share my screen again. Okay, to restart. So plus so since the heat has to add up to 0, you can just add the two equations, since on one side of the equation is everything and the other side is Q, you can just add the two equations and have them equal to 0. So then you just have to solve for T using some algebra, which I can show you as well. Minus. So then the final temperature will be around 46.627 degrees Celsius. And when you look back at the question, that makes sense because it has to be in between 30 degrees Celsius and 50 degrees Celsius. It's going to be closer to 50 degrees Celsius because there's more water that is that temperature. Okay, so we're done with this worksheet. Okay, so we are going to do some silent questions. Okay. Okay. So, question number 1. Which of the following is not required for a reaction to occur? We didn't go over like all of this, so I can explain it if you guys want to. Okay, so for a reaction to occur, the molecules have to collide with each other because that's the way that they break the bonds and then create new ones, by colliding with each other in the correct orientation and with the enough energy. So A, B, and C, A, C, and D, you all have to have those. But B, it does not have to be spontaneous, and it does not have to be exothermic. Some reactions are endothermic. And spontaneous just means that it happens by themselves, but they're clearly like chemical reactions that don't happen by themselves. Like fire, you need to start a fire by yourself. It doesn't just ignite everywhere. Okay. Which study would decrease in the presence of a catalyst? Hang on, let me turn on my fan. Okay. Okay, B was a really good guess, but the correct answer is A, because we haven't talked about catalyst yet. But a catalyst is just something that helps the reaction go faster or makes the reaction become easier, and it just is by lowering the activation energy. And remember Hess's law? Hess's law states that if you have the same reactants and the same products, the change in entropy is going to be the same. So the heat's going to stay the same. So C, E, and B will all be the same. But D and A, D would go down and A would also go down because that hump is now smaller. So there's less of a hurdle. You don't need to crash with as much energy, which can make it react faster and easier. Okay. Number 3. Is it exothermic or endothermic? Okay. Okay, so this one is endothermic because the products have more potential energy than the reactants. So that extra energy has to come from somewhere, and that's going to come from the surroundings, where it's going to absorb the energy from the surroundings. So that's what makes it endothermic. Exothermic, it would release the surroundings. So if the products is higher, that's endothermic. If the reactants are higher, that's exothermic. Okay. This one is tough because I did not exactly explain it yet. Number 4. Okay. So magnitude. Oh, we're on number 4 right now. I didn't explain this yet, so I'm just going to do it now. Magnitude is like not positive or negative, it's just like the amount, like the absolute value. And remember, Hess's law states the same products and reactants will have the same enthalpy change in heat. So B would not change the magnitude. So that removes D. And A would hang on. Okay, A would be decreased, I believe. Because the whole reaction is just flipped. So A gets okay. Yeah, that one I did not explain very well. Okay, you said B. Okay. 5. Okay, we haven't done 5, so we're gonna do 6. And for this one, you just need to know that the internal energy is work plus heat. Well, number 6. Okay. So for this one, it's just really important to know if it's positive or negative, and then you just have to add it. So the work is done on the system. It's not done by the system. That means it's being added to the system. So 600 joules from the work, that's positive. But the heat is negative because it's giving it off. It's not absorbing it. it was absorbing it, it'd be getting more heat. But if it's releasing it or giving it off, that's negative heat. So it's 600 plus the negative 250 joules, which adds up to 350 joules. Okay. We're going to do 7 now. For this one, you have to use Q equals MC delta T. So when you multiply the mass, which is 50 grams, times the specific heat, which they give you, times the change in temperature, which is 88 degrees Celsius, you get 10,736 joules. But it wants them in kilojoules, so you just have to divide by 1,000 to get 10.7 kilojoules. Okay, for number 8. Okay. Okay, for number 8, if the heat is transferred to the system, that means that the system is absorbing the heat, which means that it would be an endothermic reaction. So that crosses out A and C already. And if it's endothermic, that means that it has to absorb the energy from the surroundings because there's not enough energy to keep it going, which means that the products would have more potential energy than the reactants. So the change of the heat would be positive. Which would leave us with D. Okay, which of these is an increase in entropy? So entropy is just a disorder of a system. So which one is getting more disordered? Okay, so if the filing folders are getting organized, that means they're getting less disordered, getting more orderly. So that would be less entropy. If a substance freezes, frozen things, they have less entropy. Entropy increases with temperature. So as it gets cooler in temperature and it phases, that is also a negative sign for delta of entropy. Salt dissolving in water, that means there are more things at the end than the beginning, because the salt will separate into the ions, so that means there is positive entropy there. So the answer is C. And for D, you're getting two things and putting them into one thing, so that's less disordered, so it would also be negative sign for delta entropy. Okay, we're not going to do 10. And for 11, you just need to know Hess's law. It doesn't matter what steps they take. You just have to add to individual ones. Question, okay, for number 11, you just have to add the individual ones to get the delta H for the full reaction. So it's just negative 390 plus negative 745 kilojoules, which will add up to negative 1,135 kilojoules, which is B. Okay, so we're gonna end the class now. You guys can ask questions if you have any, or you can just like look forward to your next class. Okay, here's something that I'm wondering. What grades are most of you guys in? Oh, going to 10. That's awesome. Oh, you guys are a lot older than I thought. 9th.